Okay, Stat AP friends. Today you're going to learn about Chapter 23, which is confidence intervals and hypothesis tests for two sample means. So you'll find everything that you need in Schoology. Look at the Friday the 26th folder, and you can download the Word document, which has the notes. It looks like this, Chapter 23, two sample T intervals and tests. And then you can also download the PowerPoint, which is the answer key. And that's what I'm going to use right now to make the video. I'll use the PowerPoint. And then finally, a reminder that today you have until 11:59 p.m. Friday the 26th to finish, or I guess to submit your Chapter 22 quiz. So don't forget that. Okay, let's start this PowerPoint. There it is. Okay. So Chapter 23, two sample mean inference procedures. So I guess these are the steps of any hypothesis test. You start with defining the parameter. This time we have two samples, so we would have two parameters, mu1 and mu2. Or I like to just define them at one thing as mu1 minus mu2. And that would be like the true difference in the means of blank and blank. So that's how I prefer to define the parameters. Step 2, write some hypotheses. So your null hypothesis should always have an equal sign. So we assume that the mean of the first population equals the mean of the second population. Or you can write it as mu1 minus mu2 is equal to 0. So the difference is equal to 0. Which is the same thing as mu1 equals mu2. The alternative hypothesis could either be a less than symbol, greater than symbol, or a not equal to symbol. It just depends on the situation. Again, I like to write them as a difference. So the difference is less than 0, the difference is greater than 0, or the difference is not equal to 0. Either one is correct. You just pick one, depending on how you want to write them. Okay, the next step on every hypothesis test is to check some conditions. So just like before, the randomization condition, this time you need to say that you have two independent random samples. So now there's two of them. 10% condition, you need to say that both samples are less than 10% of their populations. And for the large enough condition, or sometimes it's called nearly normal, you need to say that either both populations are known to be normal or both samples sizes have to be at least 30 so that you can use the central limit theorem. Or finally, you need to say that both graphs look symmetrical with no outliers. So it just depends on the situation. So that is the first three steps of every hypothesis test ever. Next, you're going to do some calculations. So if you're doing a hypothesis test, we're going to find a test statistic and a p-value. If we're going to do an interval, then we're just going to use the interval formula. So here they are. This is the new formula that you're going to have to memorize. So Chapter 23 is called a two-sample t-test. So two samples because we have two samples. And we're always going to be doing a t-test when we have two samples. So this is a test statistic here, a nice big formula. And then similarly, the interval formula is called a two-sample t-interval. And this is the formula that we're going to use today in our examples. So because you now have two separate samples, so size 1 and size 2, your degrees of freedom, remember t-distributions and t-intervals require degrees of freedom. So now for the degrees of freedom, it's always been sample size minus 1. But now we have two separate samples. So here's how you do the degrees of freedom. You have two options. Option number 1 is going to be your degrees of freedom would just be the smaller of the two values, either the first sample size minus 1 or your second sample size minus 1, whichever one is smaller. You pick that, and that would be your degrees of freedom. Or my favorite option is you can just use the degrees of freedom that is given in the calculator, which is what I'm going to do. I'm going to show you on the calculator. It does some fancy formula, and it just calculates a degrees of freedom for the two samples. So that's what I'll use. Finally, the last thing you'll need to know about t-test and t-intervals for two samples is that we never use the pooled option. I'll show you what that means on the calculator, but we will not ever, we'll never ever use the pooled option for a two-sample t procedure. I'll show you that on the calculator in a minute. And then lastly, the last step is to write your conclusions. So I guess if we're doing a hypothesis test, same thing as always. If the p-value is very small, I reject the null hypothesis. There is evidence that the alternative is true. And if the p-value is large, I do not reject the null hypothesis, and therefore there's not enough evidence that the alternative is true. And always write it in context. If you're doing an interval instead, remember that you need to interpret your interval by saying we are blank % confident that the true difference in the means of blank and blank lies between blank and blank. And then if it asks you to interpret the confidence level of your interval, you say, using this method, blank % of the time, the intervals constructed will contain the true population parameter. And this time, that parameter is the difference between mu1 and mu2. Okay, so that was a lot of stuff. Now we're just get ready to do an example. So again, look at your Word document, save it, or at least save the PowerPoint. Example 1. It says, a man who moves to a new city sees that there are 2 routes that he could take to work. A neighbor who has lived there a long time tells him that route A will average 5 minutes faster than route B. The man decides to do an experiment. Each day, he flips a coin to determine which way to go, driving each route 20 days. He finds that route A takes an average of 40 minutes with the standard deviation of 3 minutes, and that route B takes an average of 43 minutes with a standard deviation of 2 minutes. His histogram of travel times are roughly symmetric and show no outliers. Find a 95% confidence interval for the difference in the average commuting times for the 2 routes. Should the man believe the neighbor's claim that he can save that on average, he can save time by driving route A. Okay, so let's do one at a time. Let's go ahead and do the interval first. So what we have here is we have 2 samples. We have a sample of 20 days from route A with a mean of 40 and a standard deviation of 3 minutes. So that would be the sample mean and the sample standard deviation for route A. Then we have another sample of 20 days for route B with a mean of 43 and a standard deviation of 2 minutes. So that would be the sample mean of sample 2 with the standard deviation, sample standard deviation for route B. So here are the steps of doing, I guess, the interval. You have to define the parameter. I always like to define it as the difference. So I'm just going to do mu A minus mu B is the true difference in mean of times that it takes to commute taking route A from A and route B. So I did route A minus route B. The conditions are going to be the same 3 conditions as always. Assume we have 2 independent random samples of days this time. So 20 days for route A and then 20 separate days for route B. So assume we have 2 independent random samples. Assume that those samples of 20 are less than 10% of the possible population. So 10%. The samples should be less than 10% of the population. So we're just going to assume that. And then finally, for the large enough condition, 20 is not at least 30. So we can't use the central limit theorem. And then the problem doesn't necessarily say like normally distributed, but the problem does say that the graph of the commuting times is symmetric with no outliers. So the problem did state that you have graphs that are symmetric with no outliers. And therefore, any sample size is going to be large enough. So we're good for that. So letter B, check the conditions. Done. Letter C. Calculate the interval. Again, you're supposed to show the formula for the interval. So this is the formula for a two-sample t-interval. You take the sample mean of A minus the sample mean of B, and then you'll do plus or minus a t-score here times the standard deviation, which will be the square root of the sample standard deviation of A squared over the sample size of A plus the sample standard deviation of B squared over the sample size of B. So that's the formula. You're going to have to memorize it. And now here are the substitutions so far. So remember that the sample mean of A, it was 40 minutes to commute, so I put 40. The sample mean for route B was 43 minutes, so I put 43. And then plus or minus, I'm about to find this little inverse t here. So what I did was inverse t of 0.975, since you were doing a 95% confidence interval, comma 33.1. That's the degrees of freedom that I'm going to get using the calculator, which again, I'll show you. So 33.1. That would give me this t-score. Okay, now I need to multiply by the standard deviation. So it would be the square root of the standard deviation for route A was 3 minutes. So this should have been a 3. Well, it's over here. Okay, I changed the order, but that's okay. So 3 minutes squared over the sample size, so 20. So this is the standard deviation for sample A. And then for route B, I did 2 minutes. So the standard deviation was 2 minutes. So here it is. So 2 squared over 20. So you have to square the standard deviations. So S squared plus the other S squared. So if you were to type all that into the calculator and do the plus and do the minus, you would get an answer, which I guess let's go do it now. Okay, so on your calculators, you can do it from a scratch pad. You need to find something called a two-sample t-interval. So menu, statistics, it needs to be an interval. And it needs to be called a two-sample t-interval. So option number 4 here, two-sample t-interval. Click on that. And then the input method, we need to switch it to stats. Since we don't have the whole data list, we just have stats. Okay. And now just repeat the process, fill in all the info. So for route A, that was 40 minutes with a standard deviation of 3 and a sample size of 20. Route B had a mean of 43 with a standard deviation of 2 and a sample size of 20. We are interested in creating a 95% confidence interval. And now here's what I'm talking about earlier. Always leave this pool thing as no. You never want to pool the two samples together. That's just not something we do for this stat class. So leave it as no always. And now press OK. And here's a bunch of info. All right. So the upper and lower bound are given right there. So that would be your answer that you would copy on your on your paper, I guess. Negative 4.64, comma, negative 1.36. So that's your upper and lower bound. And then there's a bunch of other stuff here that's given, like the margin of error. But anyway, the next one we need is this, the degrees of freedom. So the calculator somehow uses a formula and finds a degrees of freedom for these two samples, for these two sample t interval. So that's the one I use, 33.1. So that's where this 33.1 came from. So, okay, so here's the answer. So I just said it. The lower bound was negative 4.64 and the upper bound was negative 1.36. So here it is, negative 4.64 to negative 1.36. So that's one possible correct answer if you're just going to go ahead and use the calculator for the degrees of freedom. Another possible correct answer is over here. You don't have to do both. You can just always use the degrees of freedom from the calculator. Again, so that was given right here, 33.1. So that can always just be your answer. So that's your final answer. But you could also, the other option for the degrees of freedom here is you could have just used the smallest sample size minus 1 to get your degrees of freedom. So the sample sizes were both 20. So 20 minus 1 would have been 19. That just gives you a slightly different t-score here. So instead of like 2.034, you'll get like 2.09. So your interval is pretty close. It's about the same. It's just slightly different. And they're both correct. Either one is acceptable on the AP exam. You just have to show your work and write down which degrees of freedom you're using for sure. So if you're going to use a calculator, go ahead and write down degrees of freedom is 33.1, which is what I use from the calculator. Or if you're going to just use the smallest sample size minus 1, then just put degrees of freedom is equal to 19 in this case, and then show your answer. So your answer has to have the correct degrees of freedom. And that is how you do a two-sample T interval. So that was letter C, find the interval, done. Letter D, interpret the interval. So you're just going to use that wording recipe. We are 95% confident that the true mean difference between the commuting times, I did A minus B, so route A minus route B, is somewhere between negative 4.64 minutes and negative 1.36 minutes. So that is the difference in the times from route A and route B. So that's letter D, done. And now on your notes, the last one on example 1 says letter E. Should the man believe the neighbor's claim that on average he can save time driving route A? So at the very beginning, the neighbor said that he can save 5 minutes faster, but this time we're just going to answer what the question says here. We're just going to see if the man should believe the neighbor's claim that he can save time by driving in route A. So remember that we subtracted route A minus route B. So our interval was all negative. That means that the values of route A were smaller than the values of route B because we subtracted A minus B and got negative numbers. So that's basically saying that route A has smaller times, and therefore, yes, he can save time. But now here's the official proof. So you want to write some hypothesis to prove this claim. The null hypothesis should be that there is no difference between the two routing times. So the mean time for route A should equal the mean time for route B, or mu A minus mu B equals 0. The alternative should be that mu A is faster, so the mean for route A is faster than the mean for route B. So that means that the times for route A should be less than the times for route B. Or in other words, the mean of A needs to be minus the mean of B needs to be less than 0, because that just says that the values of A are going to be smaller than the values of B, and therefore have a 0 difference or a negative difference. Okay, so those are the hypotheses. And now I'm going to use the interval to prove what I just said earlier. Since the null hypothesis of 0 is not contained in the interval, that means that there is a difference between the two routing times. So since 0 is not in the interval, we can reject the null hypothesis. Specifically, we do have evidence that HA is true because your whole interval is negative, proving that the mean time for route A is less than the mean time for route B. So in other words, you have evidence that you can save time if you're driving route A. And now that is example 1. So you can, go back and watch the video slower because I speak so fast. So just put it like a 0.75 speed, and then go through your notes, fill it all out, or again, just save the PowerPoint that has the answers. So that's how you do a chapter 23 two-sample T interval. Now I need to show you how to do chapter 23 two-sample t test. So example number 2 on the notes. Let's move on. Okay, here it is. I'll just read it. 2 competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean length of time required for body absorption from brand A and brand B. Anyway, assume the absorption time is normally distributed. That'll be important. 12 people were randomly selected and given an oral dosage of brand A. Another 12 people were randomly selected and given another equal dosage of brand B. The length of times in minutes for the drugs to reach the specified level in the blood was recorded. Here are the results. So you have a little table with everything you need. So brand A, this is your sample mean and your sample standard deviation. Brand B, here's the mean and the standard deviation for that sample. So is there evidence that the drugs differ in the speed at which they enter the bloodstream? So it's just asking for a difference. It didn't specifically say one is faster than the other. So we're just going to go with like a not equal to hypothesis to see if there's a difference. So I guess we're just going to follow all the steps of every hypothesis test. Step 1, define the parameter. The parameter can be defined as 2 separate things, like the mean of 1 equals and the mean of 2 equals. Or I prefer to just define it as the difference between the 2 means. So I like to do the mu of A minus mu of B is the true difference in the mean of absorption times in minutes for brand A minus B. So I think I did A minus B again. So that's how I like to define it. You can do it however you want to if you're showing your work. So that's step 1, define the parameter. Step 2, write some hypotheses. The null hypothesis should always be that there is no difference between your samples. So, So the null hypothesis should be that the difference between mu A minus mu B is equal to 0. So there is no difference. The alternative, the question wanted to know if there was just any difference between the 2 drugs. So we just want to know if the mean of A minus the mean of B is not equal to 0. So those will be the hypotheses that we are going to check. The conditions, same as always. Assume we have 2 independent random samples. So that's what I wrote. Assume the 2 samples. So our samples were 12 people. So again, we want to assume the 12 people are independent. And we want to assume those 12 people are less than 10% of the population. So I wrote 10% condition. The samples should be less than 10% of their populations. So the populations should be at least 120 people for each drug, which I will assume. And finally, the large enough condition. Obviously, 12 is not at least 30, so we're not going to use the central limit theorem. But the problem did say that the data is normally distributed. So in the problem, it is stated that the population is normally distributed. So I guess in that case, then our samples are large enough. So the conditions have been met. So next, step 4. Now we need to do some calculations like finding the test statistic with the awesome formula and then finding a p-value. So here's the formula. The formula for a 2-sample t-test is t equals, which is going to be a t-score. T equals the sample mean of A minus the sample mean of B minus the population mean of A minus the population mean of B, which we're assuming this is 0 because that's our null hypothesis. We assume there is no difference in the populations. So this will always be 0. Divided by the standard deviations. Again, standard deviation of A squared over the sample size of A plus the standard deviation of B squared over the sample size of B. So we're just going to take all little numbers that were on the table that were given, and we're going to substitute them. So I'm going to do 20.1 minus 18.9 minus 0 divided by the square root of, this time I did it right, I did 8.7 squared over 12. So that was the right order, plus 7.5 squared over 12. And obviously, if you just use your calculator to type that in, you will get a t-score. So I'm pretending like you did super fast, and you got a t-score of 0.36. And now, to get a p-value, you're going to need to do, since this hypothesis, remember the alternative was a not equal to sign? That means that we're going to have to find the area greater than 0.36 and multiply it by 2. You need to multiply this p-value thing by 2 because our alternative hypothesis was a not equal to symbol. So the way you do that is you're going to use the calculator and you're going to do a TCDF of 0.3619, comma to infinity, because we're going greater than, comma 21.5 are the degrees of freedom that I'm going to get from the calculator, which I'll show you. And then you have to multiply by 2 because it was a two-sided hypothesis. So it's going to be a big p-value here, 0.721. Or the other possible p-value is if you'd use 11 degrees of freedom instead. So again, you take your t-score, which was 0.3619. You find the area to the right of that, greater than 0.3619 because it's positive, so it has to be greater than, comma infinity, comma, let's use 11 degrees of freedom, so just 12 minus 1, and multiply by 2, and you can get a slightly different p-value, but about the same. So let me show you on the calculator. You don't have to do both. You can just do one. Like I always just use the calculator, so I'm just going to use this one always. So here's how you would use the calculator. You would have to go find on the scratch pad, find a 2-sample t-test. Menu, statistics, stat test, 2-sample t-test. Switch the input method to stat. Again, you just have to substitute everything in from your first sample. So that was drug A. The mean was 20.1. Standard deviation was 8.7. Sample size was 12. For my second sample, which was drug B, the mean was 18.9. Standard deviation 7.5. Sample size 12. The alternative hypothesis was the not equal to symbol, so just leave it like that. You never pool the 2-sample tests together for this class, so just always leave it as no. Press OK. Didn't work. That's the other one. Oh, okay, I have to do it again. 2-sample t-test. Enter. Okay, that one worked. All right. So this 2-sample t-test on the calculator, it's going to give you your test statistic, which we already knew. It was 0.36. And remember, you can do that by actually calculating this 20.1 minus 18.9 over all this stuff. So 0.36 is correct. It's also going to give you the p-value, which has already been multiplied by 2. So the calculator, it knows that it was a two-sided hypothesis, so not equal to. So it already multiplied your p-value by 2, 0.721, which is what I wrote right here, 0.721. And now make sure you show me that, or I guess if you're showing your work, just make sure you tell the person that this p-value came from the degrees of freedom of 21.5. because the calculator used some formula and it got a degrees of freedom of 21.5. So it's important to show those degrees of freedom for that p-value, because some of y'all are not going to use the two sample t-test on the calculator. I don't know why, but some people don't. And then you'll just want to do it by hand, like type that in and get a test statistic. And then you're going to by hand do a TCDF of 0.3619, comma, infinity. And then you would be using 11 degrees of freedom, which is the smallest one of these minus 1, times 2, and you'll get a slightly different p-value. So regardless, just when you do the p-value, make sure you show which degrees of freedom you're using. They're both correct. So that was letter D and E. Find the p-value. Done. Interpret the p-value. So there's a wording recipe that you just have to memorize, and hopefully you know it by now. But the p-value recipe is, if the null hypothesis is true, then the probability of observing the given statistic is p-value %. Or, in this case, if the drugs don't differ in speed at which they enter the bloodstream, then the probability of observing the given statistic or a more extreme value, so greater than or equal to, is about 7.2%. So that's how you define a p-value. Now, with your p-value, you make a decision and a conclusion. Actually, that's not right. It's not 7.2, it's 72.4%. So let's fix that. Right here. I can't multiply by 100. 72.4. Okay. I'll try to upload the correct PowerPoint with the 72.4%. Regardless, that was still a big p-value. I mean, 72 is way bigger than 7, but still, because it was a large p-value anyway, I do not reject the null hypothesis. And therefore, there isn't enough evidence that the drugs differ in time. So that's how you do a 2-sample t-test. And to finish off the examples for today, so this is chapter 23. And if you ever feel bored, you can read chapter 23 in your book. To finish this off, we're going to make a interval for the difference of these two drugs. And then we're going to see if your interval would give you the same decision and conclusion as your test, which the answer should always be yes if you did it right. Okay. Hold on. This should have like a little animation. Okay. So letter I, construct and interpret a 90% confidence interval to estimate the true mean difference in speeds of the drugs at which the drugs enter the bloodstream. So just like we did on example 1, there's a nice formula that you should write down. There's some substitutions that you need to write down. So I did my sample mean of A, 20.1, minus the sample mean of B, 18.9, plus or minus an inverse T of 0.95 since it was a 90% confidence interval. And then again, I'm using the degrees of freedom that were on the calculator, 21.5. And then the standard deviation of A was 8.7 squared over 12 plus 7.5 squared over 12. Okay, so to get this answer, we could just use the calculator, which is what I recommend. So again, on your calculators, it's called a 2-sample t interval. 2-sample t interval. Switch it to stats. Okay, just do it again. 20.1. 90% confidence. Never pull. Just always leave it as no. Press enter. Oh, here it is. Okay. So this is my interval if I use 21.5 degrees of freedom. So you can just write negative 4.50 to 6.90 using 21.5 degrees of freedom. Again, for the last time, when you give your answers when it comes to these two sample t-test and intervals, make sure you always tell the reader or the grader, I guess, which degrees of freedom you're using. So negative 4.5 to positive 6.9 was a degrees of freedom of 21.5. And that's all you're required to do. Now, if you want to be different and use the other degrees of freedom, which is n minus 1 from the smallest sample size, so 12 minus 1, that's 11, you'll get a slightly different answer, which is also correct. And that's why, like I said, it's important that you just show which degrees of freedom you're using. So if you want to use 11 degrees of freedom, this would be your answer here, negative 4.75 to 7.15, which would also be a correct answer. And you're always supposed to interpret an interval. So I am 90% confident that the true difference in mean of speeds at which the two drugs enter the body, I did A minus B, lies between negative 4.5 and 6.9 minutes. So with that interval, like you don't know which one's faster. Like A could be faster or B could be faster because you have negative values and positive values. So you don't know which drug is faster. And that is why, yes, you will reach the same decision and conclusion as you did on your hypothesis test, because since the null hypothesis of 0, which means there is no difference between the two drugs, is contained in the interval, so 0 is in my interval, I do not reject HO, and therefore I don't have enough evidence that the drugs differ in speed. And that's the end of chapter 23. So now you just need to review chapter 23, do the homework, read the book, and then we will see each other next time for chapter 24.